Hi, my name is Jacky, and I'm here to present our work on learning active task-oriented exploration policies for bridging the sim-to-real gap. This is joint work with Saumya, Saxena, and Oliver Kroemer at the Intelligent Autonomous Manipulation Lab at the Robotics Institute. Using simulators is useful for both model-free and model-based methods, but learning and planning with simulated models typically leads to the sim-to-real gap, where the simulated dynamics don't match exactly with those of the real world. There are many popular approaches to address this issue, including domain randomization, residual learning, online policy adaptation, or fine-tuning trained policies with online data, or model tuning or system identification. Our work focuses on the latter part. So in related works, we often assume that there exists parameters that sufficiently mimic real-world behavior. And what this means is that there are some parameters that we can set our simulator to use, such that the policy trained on these parameters or a policy plan with these parameters could perform the tasks successfully in the real world. So the question is, how do we adapt policies or tune simulator parameters? There are two axes that we can use to compare existing algorithms. One is whether the exploration is done passively or actively, and the other is whether the goal is task-agnostic or task-oriented. So for passive exploration, the observations, the trajectories that we use to tune the simulator is from offline or online task execution, or for active, in the case of active exploration, the observations come from having a separate exploration policy that's explicitly generating informative observations that we use to tune our simulator. For task-agnostic, this means that the procedure is optimizing for the accuracy of the model predictions or the tuned model parameters, whereas for task-oriented methods, this is optimizing for the performance of the downstream task. Our work focuses on the intersection of the latter 2 points, which is that we want to learn an active exploration policy that is also task-oriented. And the motivation here is that we really want to focus on the parameters that have an outsized impact on task performance, and once these parameters are tuned, we will be able to use the model directly to perform the task. So how does this work in practice? Well, if we were given an active task-oriented exploration policy, the way we would use it is as follows. We would first deploy the exploration policy in the real world to generate an informative exploration trajectory. This trajectory is then given to the simulation optimization module, which would be, say, solving a linearly squares problems, or it could be doing derivative-free optimization on a black box simulator model. Once that's done, the estimated model parameters from simulation optimization are given to the trajectory optimization module, which would then use the tuned simulator model to synthesize a task policy, and this task policy would then perform the task in the real world. So this is how we would use this exploration policy. How do we train it? Well, during training, everything is done in simulation. We still go through this exploration to task policy pipeline, and we train the exploration policy via model-free reinforcement learning, where the reward function is the performance of the downstream task policy. This performance is evaluated as an expectation over different environment and task parameters. Doing this allows us to train an exploration policy that generalizes across different environment parameters and different task parameters. We perform experiments on a variety of tasks, including a simulated linear quadratic regulator task and 2 real-world robot tasks that are pouring and box tracking. These tasks have different instantiations of different parts of our framework. For example, for the model, the linear quadratic regulator task and the pouring task have analytical and differentiable models that we can directly optimize through. Whereas for the box tracking task, we're using a black box non-differentiable fluid dynamics simulator, and we're optimizing that with derivative-free optimization. Just to show the different exploration policies could be more or less informative, in this video for box tracking task, each row has a different physics parameter and each column is using a different exploration policy. So you can see on the leftmost column, the trajectories look the same, even though there are the parameters, the underlying physics parameters are different. And in the rightmost column, you can see the resultant trajectories are really quite different from each other, and that allows us to infer the underlying physics parameters. Our experiments show that across the tasks that we tested on, task-oriented exploration leads to better task performance than task-agnostic exploration. And for more details, please see our paper. Thank you.